But in reality, the challenge is that we don't get to observe what happens to a patient with treatment and without treatment. This is the fundamental problem of causal inference. Let's say for a patient in real life, we follow what happens to them when they don't get a treatment. In this case, we would observe that in a year, the patient has a heart attack. But we don't get to observe what would have happened to them had they got a treatment. We don't know what their outcome would have been. The outcome that we observe is called the observed or the factual outcome, and the outcome that we don't observe is called the unobserved or the counterfactual outcome. So let's say we have a group of patients, and for each patient, we observe whether they got treated or not, which is given by WI. So for patient 1, they got treated, and we observe their outcome under treatment, and that's given by Y of 1. We don't get to observe their outcome under control, and we also don't get to observe their difference in outcomes because we don't know one of the two outcomes. And that's the case with every other patient in the group where one of the outcomes is unknown, hence the difference in outcomes is also unknown. So with this in mind, how do we actually estimate the average treatment effect, which is given by the following expression, when we don't know any one of the individual differences in outcome? It turns out that we can compute the average treatment effect when we're dealing with data from randomized control trials. If the data does not come from randomized control trials, then we often cannot apply the following idea without making strong assumptions about how the data is generated. The basic idea is to group all of the patients who get the treatment together and those who don't together. Then we take the mean of their observed outcome. So here we observe that the fraction of patients who have an outcome is 0.32. And here, when we take the mean of the outcomes for the patients who were in control, we observe that the fraction of patients who experience an outcome is 0.51. Then we can compute the average treatment effect using the following expression, where we can look at the expected value of yi when wi equals 1, and this is given by 0.32 right here, minus the expected value of yi when w equals 0. So this is using this table here. What's the average of the yi values? That's 0.51. And so we can take the difference between these two to get an average treatment effect of negative 0.19. So we just computed an average treatment effect of negative 0.19. This value of the average treatment effect is closely related to another measure of treatment effect that we saw earlier, which is the ARR, or absolute risk reduction. And the ARR is simply the negative of the ATE. So our ATE is negative 0.19. Our ARR is 0.19. Remember that the ARR tells us that the average reduction in risk with treatment is 0.19 or 19%. So we can use randomized control trial data to estimate the average treatment effect. While this is useful, really we'd like to make a more individualized estimate to determine what is the effect of treatment on one particular patient going to be.